In the previous lesson, you improved the line tracking behavior using the encoders to control how far the robot would follow the line. As a consequence, you now also have the ability to optimize the behavior for different sections of a line tracking course. Take this course for example. The first section is mostly straight. Now let's examine the code. We haven't been paying much attention to the motor power levels we're using, but combinations of 0 and 40 cause the robot to perform sharp swing turns. Sharp swing turns aren't needed to keep the robot on a mostly straight path, so the robot is actually wasting some effort overcorrecting itself down the line. We can eliminate most of the wasted effort in this section by choosing motor powers that are closer together, say 40 and 20, to create less drastic swing turns. Before making the changes, save your program as line track for distance, optimized. Now replace the 0 motor power levels in the first and third if statements with 20. Compile and download, and run. The robot moves down the straight portion of the course much more smoothly. But what about this section, with sharp curves and bends? Power levels of 20 and 40 probably don't create sharp enough swing turns for the robot to track these kinds of lines. In your program, starting with the threshold assignment, copy the line tracking behavior, and paste it below. Be careful to add the copied behavior after the first, but before the closing curly brace of task main. We now have 2 full line tracking behaviors in our program. The first is optimized for the straight portion of the line tracking course. Let's optimize the second behavior for the section with sharp curves and bends. Everything from the threshold value, number of encoder counts to track, and the motor speeds can be modified. The line in the second section is the same color and in the same lighting conditions, so the threshold value is probably okay. Let's make an educated guess that this section will take longer to travel due to the curves and bends, and increase the number of encoder counts in the condition to 1,800, 5 rotations. To account for the sharp curves, we'll want the robot to make sharp swing turns. Replace the 40 power levels in the first and third if statements with 60, and the 20 power levels with 0. Compile and download, and run. The robot continues to track the first section smoothly with the 40-20 power levels, and does a great job tracking the second section with the 60-0 power levels. So line tracking on straight sections can be optimized using gradual swing turns made up of similar motor power levels, and on curvy sections with sharp swing turns made up of very different power levels. Simple enough, right? Try practicing your newfound knowledge on a line tracking course of your own. Some pieces of advice as you do. Try to break the course down into several sections, based on how curved each section is. Don't try to program the entire thing all at once. Perfect the threshold, number of encoder counts, and motor speeds for the first section before moving on to the next. Each behavior will probably be made up of the same exact code, with the only differences being in the values used. Sounds like the perfect opportunity to implement a line track function with parameters. In this lesson, you learned how to optimize the line track behavior for different sections of a course. Fantastic! You're now several steps closer to being prepared for the grand challenge.